Um, we're going to talk today a little bit about the history of AI, um, thinking about the history of computers in general and how this is related to this idea of artificial intelligence. In the early days of computing, we didn't necessarily have this phrase, artificial intelligence, but a lot of the ideas of computing are relevant to our contemporary ideas of what AI is. And this class is designed to think about how those two things connect, as well as how those things connect to the process of art making and ideas of art making. So to understand the history of art and AI, we really need to start with the history of computers and what might be the earliest examples of generative artwork and early experiments in generative artwork, which is what we would have called this stuff rather than AI. We might have called it generative or even cybernetic artwork. And we'll get to some of these distinctions in a moment. But let's start with something really basic, which is this fundamental question of what exactly is a computer? I want to start here in 1914. That's the year that Torres Quevedo created a machine that could play chess. The first model could only play a specific endgame. So here you see just two rooks and there's two kings initially, two rooks and two kings. In 1917, he invented another model where the pieces would move using electromagnetics. The machine was even able to speak. It would tell players when they had broken the rules, and it would reset the game if its opponent made 3 illegal moves. And it did this through a little phonograph record that would play when it made checkmate, or the player made checkmate, or broke the rules. The automated chess player was able to do this through mechanics. That is, there's a series of rules enforced through the design of gears. So over to the right, you see this illustration of how these gears laid out. And this was a physical constraint on what was possible with the interaction with the machine. You set these mechanics up underneath the board, and you place these pieces magnetically, and it's a matter of clockworks. Sliding pieces moves gears, which locks other gears, and so on. And I suspect when we talk about things like game mechanics in video games, we're talking about the same kind of thing. An unseen system that controls the moves of the game, determining the start and finish of play. The chess player wasn't just the first working game-playing automaton. It was also the first real computer game, however limited it was. And today we might think of it more as a clock game. But computers, as we're going to see, it's one of those words that changes over time. And artificial intelligence has the same kind of evolution. This game was limited by its literal mechanics. The complexity of playing a game beyond 2 pieces would have been astronomical because of how intricate the gears would need to be. You're looking at the gears for just 4 basic pieces, right? 2 sets of identical moving pieces. Think about what this would have been for a full game. It would have been exponentially more difficult to build using mechanical clockwork systems. And this is the constraint on mechanical thinking that inspires a whole range of computer scientists to think about new ways of calculating and solving problems. If you can't do it through mechanics and clockworks, how can you do it? And this is where I would say is the start of thinking about computational systems, or at least it's the logic that drives the thinking behind computational systems. So in 1936, Alan Turing writes a paper to solve this interesting problem. To really understand what Turing did, it's also important to understand that computers in 1936 were human beings. And that definition really held true up until the 1970s. This image that you see on your screen is the computer room of the US Veterans Bureau in 1924. So if you've seen the movie Hidden Figures, you may be familiar with human computers. This is the computing division, right? Basically, with things like NASA, for example, you would have physicists, engineers, mathematicians working on kind of theoretical concepts. And these concepts would then be handed to a room full of people, usually women, who did the actual calculations. And Turing was interested in how to build a machine that might be able to turn these conceptual abstract theories into the appropriate math without people. How do you replace human calculation with mechanical calculation? The result is called a universal machine, later called the Turing machine. Now, Turing never built this thing, which is why we call it a theoretical machine. But it proposed a framework for eventually building what we would recognize as computers today. And here's a video to explain how Turing thought it might work.
Alan Turing. You may know him from such films as The Imitation Game or the biggest award in computer science called the Turing Award. At the young age of 22, Turing got intensely interested in this last question, decidability. Did there exist an effective procedure for deciding the truth or falsity of any mathematical statement? But Turing saw a slight problem with the question. What exactly was an effective procedure?
Today, an effective procedure is considered to be an algorithm, some step-by-step set of instructions that you can follow without using any real thought or intuition. But this was back in the 30s, and the idea of an algorithm was still vague and ill-defined. We're used to the concept now because they're fundamental to how computers work, but computers didn't exist back then, or at least not as we know them today.
The word computer referred to people, usually women, who were given a list of instructions and carried out tedious computations by hand. This job required little thought and definitely no mathematical intuition. Throughout his life, Turing was fascinated with the relationship between humans and machines. He's famous for coming up with the idea of the Turing test, a test for determining whether a machine is capable of thinking like a human. This was no exception, as the term effective procedure was too vague to do anything rigorous with. He decided to define it himself. He based his definition on a human computer. He decided that anything a human computer could do by mindlessly following a list of instructions, using no genius or insight whatsoever, was an effective procedure. He thought about the basic components of what a human computer does when they're computing. 1. They read instructions. 2. They read and write symbols on a piece of paper according to the instructions. 3. They occasionally erase symbols and replace them with new symbols. And 4. When they're finished with the computation, they stop. That was about it.
And here is where the truly revolutionary part comes in that would transform the world for years to come. Turing recognized that every step of what a human computer did could be replicated by a very simple theoretical machine.
In place of the human could be a scanning head, which could read one symbol at a time, erase one symbol at a time, and write one symbol at a time. The piece of paper could be replaced by an infinitely long piece of tape, which contained one symbol per square.
But how does the machine know what to do?
When a human reads a set of instructions, something is going on in their mind which tells them what to do next. Turing thought of these as states of mind. And so similarly for his machines, devised the idea of internal states, which tell the machine what to do. This idea is best understood using visual diagrams and an example. Say we want the machine to perform the very simple task of recognizing when there are an even number of zeros and ones in the tape. This is easy for a human who has mastered the art of counting, but it's not so straightforward for a machine. A simple way for our machine to tackle this problem is to pair a 0 with a 1 and then cross off the pair with an X. It keeps doing this until it can't anymore. If it crosses off all the symbols in the tape, we'll know there was an even amount. If it doesn't, we'll know that there wasn't. Now, how do we program our machine to carry out this task? Well, we build it with an internal state table that looks like this. I know this looks complicated, but it's not too bad. Let's read it together. Take this tape with these symbols. We want the machine to tell us whether there is an even number of ones and zeros. The machine starts in the start state. The start state tells the machine, if I find a 0, I will replace it with an X, move to the right and into state B. If I find a 1, I will replace it with an X, move to the right and into state C. If I find an X, I'll leave it alone and stay in the start state. If I don't find any ones or zeros and only encounter blank squares, They must have all been paired up, so I move to the accept state. So at the moment, our scanning head is in the start state. It reads a 0, replaces it with an X, moves 1 square to the right and into state B. Now the machine has just seen a 0 and needs to find a 1 to pair it with. So state B says, if I see a 0 or an X, I'll leave them alone and move right 1 square and stay in state B. If I see a 1, I replace it with an X and move to state D. So our scanning head reads a 0, moves 1 square to the right and stays in state B. Now it reads a 1, replaces it with an X, and moves 1 square to the left and into state D. State D is only entered when a 0-1 pair has been crossed out by X's, so the machine needs to reset for the next count. It says, I keep moving the scanning head to the left, ignoring everything. If I see a 1, I leave it as a 1. If I see a 0, I leave it as a 0. And if I see an X, I leave it as an X. I keep moving until I reach a blank square, which indicates I've reached the beginning of the list of symbols. I then move 1 square to the right and go back to the start state to repeat the whole process. After another round of this, the machine only encounters X's, so keeps moving right and remains in the start state. When it reaches a blank, it moves into the accept state, and we know that this list of symbols does have an even number of 1s and 0s. So that's how one of these machines would work. But here, Turing had another incredible insight. See, at the moment, you would need to build different machines to do different tasks. A machine to calculate square roots would need to be built with a different internal state table than a machine to do addition. But Turing realized that any internal state table could be encoded into a list of 1s and 0s. In this way, we could feed the instructions as well as the problem into a new machine, and that machine could perform that set of instructions. Today we know this as a programmable computer. We have computers which we can program to do different things after they've been built. That idea originated right here in Turing's paper.
So, by 1937, Turing starts talking to another scientist, John von Neumann, about the possibility that the human brain might act in a similar way to this Turing machine. And von Neumann makes some major contributions to computer science based on the idea that the brain works like a machine. And this is where this idea of the Turing test comes along. Can you make a machine that could confuse an interviewer about whether it's human or not? So around this time, Warren McCulloch and Walter Pitts proposed something called a neural network. And they were doing this not to build a computer, but to argue that the human brain worked like a machine. They understood machines of their era, and they started grasping at ways of applying machine metaphors to human thinking. The neural net works like this. The neuron is in your brain, and certain things activate that neuron. These are things we might consider variables. Neurons have to fire chemicals or not fire chemicals in order to send information to other neurons. So picture this image as one part of a vast network of neurons in your brain. Each neuron has to make a decision, and each neuron fires or doesn't fire according to certain thresholds. So here we're using 3 variables to keep it pretty simple. If any of these 3 conditions are met, the neuron might fire based on what the threshold is. Then the other half of the neuron, this threshold measurement, takes that sum and sends it along as information to the next neuron. This is basically a children's book explanation of this. So I encourage you to dig a lot deeper into neural nets. But I wanted to give you a very, very rough idea of how these work in theory. So how does a neural net make the decision of whether to eat some pizza on a table in front of you? Again, the information in a neural network isn't as clear-cut as this, but this is designed to be a really simple overview. Let's say you're hungry and your threshold to eat pizza is 1. To represent this as a neuron, any of these factors would be enough to predict that you're going to eat the pizza. Whether you're hungry, whether there's free pizza, and whether you like pizza. If any of these conditions are met, you might eat the pizza. So here your threshold is the 1, or this is we'll connect this here. Your total is the 1 because one of these things is true. You're either hungry or there's free pizza or you like pizza. And your threshold might be 3. But you're actually, all three of these things are what you want. You're hungry, you're free, there's free pizza, you like pizza. So you only needed one of these to be true, but three of them are true. So you're definitely going to eat that pizza. This makes sense? So let's say you're hungry, but you're extremely polite. There's pizza on the table, but no one's offered you any. And so now you have two criteria as a threshold to fire. You are hungry and there's free pizza. So you have two of the variables in your threshold are met, but you need three. Your actual threshold is 3 in order to fire. And you haven't been offered the pizza, so you're not going to eat the pizza, right? Now, this arrangement would essentially require that all of the variables would be met before passing on the information. So this model of neurons and perceptrons, and again, that was a real simplification, but this model of neurons and perceptrons was remarkably agile, not just for thinking about the human brain, which was the goal. Remember, this was scientists taking the metaphor of a machine, trying to explain human decision-making with it. Later on, computer scientists would look at this model of the human brain and they would use it to replicate human decision-making in machines. And I say this because there's something pretty important going on here. Scientists looked at machines to model the human brain, and then years later, other scientists looked at that model of the human brain and used it to model computers. But this is just one model of how the human brain works, and it's a model that's based on the way machines work. It's a comparison, it's a metaphor. It isn't necessarily the only way that we can explain how brains work. Now, maybe these are explainable, but what we're basically getting at is this is a very mechanistic way of looking at how human beings behave and act. And this was common of the era. So this is a model of its time. And it isn't the only model out there for how human psychology works. But this is the relationship between neuroscience and artificial intelligence and how it started. Now, the neural network model was actually pretty widely ignored until it was picked up by a guy named Norbert Wiener. And during World War II, Norbert Wiener was a mathematician and electrical engineer at MIT, and he was tapped to solve the problem of tracking airplanes. The UK, in particular, was constantly under siege from Nazi air raids, including a 256-day stream of air bombing over London. The US asked Wiener to develop a technology that could prevent these attacks. So he went about it by looking in an unusual place for the time, which was information theory, the stuff we're talking about. To better build an anti-aircraft mechanism, he looked at the interaction between the gun and the pilot as an exchange of information. So this is interesting, right? The idea is that the gun that's shooting at the pilot and the pilot who's flying the plane are exchanging information. The gun fires and the pilot acknowledges it, and the pilot changes course. The gunner who's firing this gun readjusts the gun and then shoots again. The pilot readjusts course based on the information of where those bullets are coming from. So this is a bit bleak, but Wiener articulated this as a feedback loop. He saw the machine as a tool for mediating a feedback loop to the advantage of the gunman on the ground. And the gun worked through mechanical means. It was able to regulate and anticipate the action of the gunman and adjust itself accordingly, so it could reduce the time needed to recalibrate and fire. And again, this is done mechanically. It's done through this clockwork mechanism like we saw on the chessboard, not digitally, not computers. You would follow the aircraft with a sight to calculate its speed, and if the shot missed, the machine would begin to reset and adjust to a new position based on the speed of the aircraft. And if the plane visibly changed course, you would stop firing, recalibrate the gun, and then refire, and the gun would sort of learn again the speed of the aircraft. So, started with weaponry, started with the military, this information relationship. This feedback loop later would become the heart of cybernetic decision-making, and Norbert Wiener actually notoriously or famously, decided he wasn't going to use this technology for weapons anymore. It was too dangerous, as he saw it, to consider after seeing what happened with nuclear weapons. He was so dismayed that he focused his energy on peacetime applications. And so this feedback loop became the heart of what became cybernetic decision-making. So this is the idea: you input into this crosshair, that information moves into the space where it adjusts the gun. And then if you hit the plane as your output, that's success. And you restart on a new plane, you go back. If you fail, that information goes through, you don't hit, and it goes back and it recalibrates. In step B, the machine adjusts itself, predicts the plane will be next, refires, checks, tests again, you either hit or you go back. Okay, so this is the feedback loop. And this feedback loop in machines, it came to dominate Norbert Wiener's thinking. He started seeing feedback loops everywhere he looked. And here we see him in the mechanical chess player we talked about earlier. Through publishing his work in this area, Wiener was able to garner enough interest that a conference was held, the Macy Conferences, which started in 1941. And in 1946, it pivoted to this new idea that Wiener was popularizing called cybernetics. Cybernetics comes from this word Kubernetes, which is a Greek word that was used mostly to think about the steering of a ship. Wiener was inspired by early technology of steering. This is called a governor. It's a bit of machinery designed to control the speed and direction of steam engines. As the boat moves forward quickly, a spinning wheel would accelerate from the speed of the current beneath it. So you have this little sort of sensor underneath the boat. And as the boat is moving forward, it spins, and the spinning wheel would accelerate if the current was moving too quickly. So if it's moving too quickly, it pushes this lever, again, all through mechanics, clockworks, and it closes oxygen off to the steam. So if the boat's moving too fast, it would automatically slow down. If the boat's moving too slow, the wheel would spin slower, and so the mechanism would allow oxygen into the steam engine, speeding it up. And this was a self-regulatory cycle. It comes from a mechanical history, but would quickly come to define the way computers would be built, and especially shape the early field of what we would call artificial intelligence. Because in essence, this was a machine that could figure something out on its own. So the idea that drives the cybernetic conferences is that information moves through systems, and the systems respond to that information. The participants were interested in the question of how these systems respond and if it would be possible to build systems that adapt the way that a biological system adapts. So they started thinking about these feedback loops in different ways. They took this simple idea of the responsive steam engine governor and they abstracted it. They were able to zoom out and do a more general frame: sensing, comparing, acting. Your ship has a goal, but it senses when the path is interrupted, it compares its new speed and direction, and then it acts, it recalibrates speed and direction. And you can connect this idea to the idea of McCulloch and Pitts. Variables enter the neuron and influence the neuron to act in certain ways, like steering a ship. So this abstraction was helpful because the cybernetics conferences were trying to do something unique for the time, which is to bring people from all different disciplines to the same space. This included mathematicians, anthropologists, psychologists, engineers, biologists. And because these fields had been so specialized, they had some early difficulty communicating with one another. The language of a biologist and the language of an electrical engineer were terribly disconnected. In every system, people would see feedback loops, though, and they could use that to describe how their systems worked with one another. And they could talk about what influenced those feedback loops and how to draw common maps. And so there's a direct lineage to this idea of making a computer that could act like a giant electrical brain, for example. The neural network got repopularized through this integration with cybernetics. And so did things like the idea of ecological systems, because you had biologists, botanists, and meteorologists talking to one another, and they could see how weather and plant systems and animals were all part of one interconnected system, which they always knew, but now they were able to sort of communicate this to one another. So the next step in all this is to build models that could represent these complex interconnected systems. So cybernetics began to create computer simulations. Computers had started emerging independently around this time in the sort of more modern sense that we know them now. So here is ENIAC. And the goal is basically to build models that could calculate not just the mathematics of business machines, but the mathematics of autonomous machines, machines that could move around freely or choose their own problems and their own way of solving these problems. These early computers were just mazes for electricity. Instead of gears, you had electric voltage moving through them that would move through circuits, get stored in certain places, and released at certain times when certain thresholds were met, similar to these neural networks, right? So they're modeled after these neural networks, and they're using electricity and storage of the electricity in vacuum tubes to sort of release and simulate more complex relationships than you could do with gears and clockworks. In ENIAC, electricity moved into 18,000 vacuum tubes, and it was stored there until certain conditions were met. And then through just sort of the natural conditions of the way electricity and energy moves, these conditions would be met and released, stored, triggered in certain patterns, etc. Right? So think back to that neural net. When this threshold hits a certain condition, it releases that energy. And a computer works by calibrating a series of signals to connect or disconnect circuits, on or off. We call them 1 and 0 today, but on a physical level, these early machines understood them as the presence or absence of electricity in a tube or moving through the system. Later, it would be light passing through a hole punched into a punch card. And light was either moving through the hole or stopped by the card. So we'll jump ahead a bit because we have this idea of light and the circuit and tubes, and we'll talk about the rise of complex modern computing. We're going to watch this video from Charles and Ray Eames from 1953. This was produced for IBM, and it's talking about telegraph systems. The telegraph was an early series for communication, and it's a physical interface for sending information, again, through electricity. So the Morse code signal is transmitted by tapping, according to Morse code, which is not exactly ones or zeros. It's lines and it's sort of dots and dashes, right? Quick taps, long taps. This video explains how that moved to computing, and it's a very good presentation of how this binary logic of on or off can become incredibly powerful as you increase the ability of a machine to process those decisions. So let's take a look.
The message being transmitted here may be unlimited in the range and the subtlety of its ideas. Yet the method and the signal are such that they must be fed to the transmitter in a series of positive decisions. The system calls for the key to be either up or down. The code calls for a dot or a dash. The current flows, it ceases to flow, it flows. It is black or white. It is stop or go. On or off. One or none. Go or no go. Or black or white, as in this small area from a halftone reproduction in a magazine. The press that printed it is capable of printing but one color of ink at a time, in this case black ink on white paper. In order to transmit the image, it had to be broken down to many points of decision, black or white. We know that such a limitation is not at all restricting if enough decisions are made. In this case, 500,000 decided points give fair rendition. 1,000,000 would be better. Conventional printing of color is no different except that with the added factor of color, 4 times the number of decisions had to be made. One set in yellow, one in red, in blue, and in black. Whenever added factors in a problem are recognized, the number of decisions necessary for the solution grows by large leaps. As theories and equipment and men develop, it becomes apparent that one sure way of handling multiple factors is to build a system that can handle each decision in its time. Men have long known the theory on which complex problems of many factors can be solved, but the number of decisions, the calculations necessary were prodigious, and not until the recent development of the electronic calculator could these areas be touched. The problem became one of communication between man and machine, between machine and machine, between machine and man. The chords are punched or not punched. Light passes or stops. And by this binary system, information is fed the machine. In a moment, we will hear sounds which are an actual product of a huge calculator. The frequencies are made audible to check its functioning and, in a way, feel its pulse. Here it is.
But through this binary system, information is fed to the machine. And as it processes this information, the more information it has, and the quicker it can compute this, the more decisions it can make. And I want to highlight that word, decisions, because we're already talking about machines making decisions. Now, what's actually happening is electricity is moving into vacuum tubes, and that vacuum tube is storing that information until certain conditions are met and then releasing it. That's what we're considering a decision. But a decision is kind of a human behavior, right? Decision making is, in a way, an intelligent decision. And so this frame of artificial intelligence, as we call it today, we think about it as decision making, and we think about it as decision making through this series of questions, on or off, right? Very densely packed. You move from one, the sort of black and white that you see in this image, with 16 million dots. Later, you have 4 colors, right? And so you get more detail and more richness and more density to the information, because those decisions, as we're calling them, are more densely packed. They're tighter, right? So you get a better, more clearer picture here printed. But with a machine, what are the decisions it's making, and how is it making those decisions, and why are we calling that a decision? This is all tied into this early days of computing, where we're thinking about replacing human computation with automated computation, right? That's decision making, and that's what a decision making machine is. So here we start seeing these inklings that frame the way we think about and talk about artificial intelligence. We're finally at a time where we might introduce art to this historical record. In 1947, Popular Science Monthly, a magazine, published an article about the strange shapes produced by television test equipment. And they suggested that industrial designers might someday turn to these abstractions for inspiration. Computers in that era were all, as we saw, electrical signals moving through devices, sometimes into screens, and they're writing information directly, right? And this electricity hits your screen and it shows up as light on your screen. And television test equipment drew lines based on the electrons coming out of whatever they were measuring. So they represented that information as electrons. You just literally had a screen that lit up when electrons hit it. And those electrons reacted and made certain shapes or lines on the device based on the strength and intensity of those electrons. It's not exactly what we would call a computer today, but it kind of worked the same way that computers of the time did. And so can you use these shapes and weird distortions of these shapes to make interesting things? Hence the name of this Popular Science magazine article, Even Necktie Designers Can Use Electrons. In 1952, Ben Laposky found this article and went about using an oscilloscope and a long exposure camera to document the movement of these electrons on the screen of test equipment that he had available. And he called these oscillons. The results of this experiment is held up as inspiration for computer art that would follow. The waves of the oscilloscope were captured onto the film negative, and then they were developed, and they looked like this. On the computer screen, interestingly, on the test screen, these would be in motion. So actually what he was creating was sort of generative video art, but he couldn't document that at the time. He didn't have a movie camera. He had a photographic camera. So he photographed these as still images, and he started showing them as artworks. Now, this may or may not fit your criteria for computer art, but it was certainly an early example of electronically generated art. And it was built on these cybernetic principles of feedback. Something goes into the television screen, and then something else goes into the television screen, and these two things interact, and they are responding to one another. So it's up to you whether you think this is computer generated. Arguably, it doesn't fit today's definitions of computers, but there was some electronic generated artwork happening here. Now, meanwhile, computers started to get more sophisticated, and we can jump way forward in time now to the IBM 360. That's the device you're looking at. This was considered small and lightweight for the time. They did math on tape, these wheels on the towers you see on the back, and this was an evolution from the punch cards that you saw in the video just then. But it's still modeled on the idea that zeros and ones are stored as information on tape. This is a pretty ramshackle device. It's bulky. It looks kind of cool, in my opinion. It's bulky, though. It's heavy. It's difficult to maintain. But these electronic calculators also offered a very new way of thinking about information. People could sort massive amounts of information. They could organize massive amounts of information, and they could communicate it. And so they started thinking about how to do that in the most efficient way possible. So by the late 1960s, you started seeing computers, machines, and electronics reach a level of sophistication where artists started to think about them and have access to them and actually be able to learn how to use them. In our first artist talk, which you'll hear this week, you're going to hear about one of those people, Gordon Pask. Pask was a cybernetician who created something called colloquy of mobiles. And there's others too. We're going to look at some of them today. But before we get to images, I also want to talk about the early days of quote unquote artificial intelligence that came about through conversations. And so we're going to talk about something called Eliza. In 1964, the computer pioneer Joseph Weizenbaum, who had designed computer systems for banks throughout the 50s, created a computer program that would allow people to speak, or rather type, with a computer and have a computer respond. And Weizenbaum would almost immediately come to regret it. Eliza was modeled on something called Rogerian therapy. And Eliza is basically a kind of psychology that you might see parodied on sitcoms, where a therapist simply reframes your statements back to you in the form of a question in order to get you to speak more deeply about your thoughts, feelings, and perceptions.
Does it understand what it's doing in the sense that we do? It's easy to leap to false conclusions, as Professor Weizenbaum discovered when he created Eliza. Eliza is a computer program that anyone can converse with via the keyboard, and it'll reply on the screen. We've added human speech to make the conversation more clear.
Men are all alike.
In what way?
They're always bugging us about something or other.
Can you think of a specific example?
Well, my boyfriend made me come here.
Your boyfriend made you come here.
He says I'm depressed much of the time.
I'm sorry to hear that you're depressed.
It's true. I am unhappy.
Do you think coming here will help you not to be unhappy?
The computer's replies seem very understanding, but this program is merely triggered by certain phrases to come out with stock responses. Nevertheless, Weizenbaum's secretary fell under the spell of the machine.
And I asked her to my office and sat her down at the keyboard, and she began to type. And of course, I looked over her shoulder to make sure that everything was operating properly. After 2 or 3 interchanges with the machine, she turned to me and she said, "Would you mind leaving the room, please?"
And yet she knew, as Weizenbaum did, that Eliza didn't understand a single word that was being typed into it.
You're like my father in some ways. You don't argue with me.
Why do you think I don't argue with you?
You're afraid of me.
Does it please you to think I'm afraid of you?
My father's afraid of everybody. My father's afraid of everybody.
The experience was quite a shock for Weizenbaum. He knew the computer had no capacity for understanding what was being said to it, and he saw people who had worked on the project and knew how it worked being sucked into these long conversations with it. And he watched his colleagues, against his wishes, started heralding it as something it absolutely wasn't. Here from Abiba Berhani's article about this called Fair Warning, extract from the essay. Here's the quote. Although he was explicit that Eliza had nothing to do with psychotherapy, others, such as Stanford psychiatrist Kenneth Colby, hailed it as a first step toward finding a potential substitute for psychiatrists. Weizenbaum's colleagues, who supposedly had a sophisticated understanding of computers, enormously exaggerated Eliza's capabilities, with some arguing that it understood language. And people interacting with Eliza, he discovered, would open their heart to it. He would later write in his book, Computer Power and Human Reason, From Judgment to Calculation, 1976, that he was startled to see how quickly and how very deeply people conversing with Eliza became emotionally involved with a computer, and how unequivocally they anthropomorphized it. He would ultimately criticize the artificial intelligence project as, quote, a fraud that played on the trusting instincts of people. So here we see for the first time how the imagination creates a relationship with a computer and becomes immersed into the story that's being told by this feedback, by this interaction. And we start to see this trusting instinct, this sense of belief in the screen and what it shows us as being an incredibly powerful tool for storytelling and interaction and imagination. But it also shows us how important it is to think carefully about the way these tools are used and toward what ends we deploy them, and also how we enter into relationships with them, how we ourselves think about what's going on the other side of the screen or the interface. So you may have heard of GPT-3 or GPT chat. These technologies are even more sophisticated than Eliza, but I want to highlight here that even from the earliest days of interaction with machines, people projected intelligence and understanding onto them. And if you think about it, Eliza isn't a person, and today's tools, again, they're significantly more sophisticated. They can make billions of more decisions using this language that we learned from that Eames film, but the fundamental principle is the same. We are the ones creating the illusion of a conversation with the information on the screen. So let's move to 1968. To bring you up to speed on where we are with the idea of artificial intelligence, by the late 1960s, the AI pioneer Marvin Minsky has told Life magazine that, quote, 3 to 8 years, we will have a machine with the general intelligence of an average human being.
Open the pod bay doors, please.
So back then, you had people saying things like, AI's just around the corner. Minsky would have had us at full artificial intelligence by 1978. It didn't turn out that way, but people were excited. 1968 is important for AI art also because it was the year that we met one of the first sentient AI robots, even if that robot appeared in a science fiction film. This is HAL 9000 from Stanley Kubrick's 2001 A Space Odyssey, part of the general exuberance / fear of artificial intelligence at the time.
Hello, Hal, do you read me? Do you read me, Hal?
Affirmative, Dave. I read you.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
Where the hell did you get that idea, Hal?
Dave, although you took very thorough precautions in the pod against my hearing you, I could see your lips move.
So there's a bit of an AI fever in the air, something I think we're in the midst of today as well. But back in 1968, Jasia Reichardt is a curator at the ICA in London. And in 1968, there's a lot of interest by artists in generative techniques. So we want to talk a little bit about what's happening in the art world at this time. For one, you had movements like Fluxus, which came about in response to John Cage. John Cage had written a piece called 4 minutes and 33 seconds, where he came out on stage during a concert of new piano music and simply sat at the piano for 4 minutes and 33 seconds. Now, Cage has articulated what this was all about. It was about changing the way we listen to the idea that music needs to be performed and written by a composer with the audience simply sitting still and enjoying it. Cage said something else. He said, there's already music all around you. Tune in, figure out how to listen to it and how to recognize the coughing and the footsteps and the passing cars of a silent concert hall as if they were the music. Listen to your own thoughts. Basically, creating space for a new way of engaging with music with the audience, between the audience as listener and the audience as producer. Now, Fluxus was a loose group of artists. It was international in scope, and they also responded to this idea that Cage set in motion. And they were very interested in the idea of taking artists out of art production. Now, they were protesting a very different sort of art world at the time. This was where art still had a tremendous amount of power in culture. Curators and museums were very tied to billionaire philanthropists. It was quite exclusive. The idea that anyone could make art was pretty radical at the time. Now, today, we see this is quite common. Social media networks are designed to facilitate this idea that anyone can write, anyone can produce, anyone can make things, and it's all valid as artistic expression, right? But at the time, this idea was still kind of radical. It had earlier roots. You could look to things like Dada, but this is 1968, and this is what's going on. They were in favor of what they called democratizing art, which we want to pay attention to because we hear this idea a lot with AI-generated art. But a lot of their work, for example, the way they interpreted this idea of democratization of art was producing things in series. So you make 100 of the same thing in order to make them more accessible to people. They'd also do these performances where they would craft situations. They called them events. George Bracht pioneered this practice, writing as short instructions on note cards and allowing people to have them as instructions for producing their own work. Most of this art was pretty surreal, pretty silly, intentionally. The idea was to make art valueless, after all. Here's an example of Brecht's work that we see on the screen. This is a direct response to Alan Turing's Universal Machine that we saw earlier, and this is called Universal Machine 2. And it's a box of more or less random images and words that are cut from newspapers and encyclopedias. Objects are in there, numbers are in there, and the instructions suggest the user should close the lid, shake the box, and reopen them to find new arrangements of words, ideas, and pictures. And it's a bit of a criticism of Turing's idea of logic as the organizing pattern of human thought. And Brecht is replacing this with chance and randomness. In the 1960s, you also had the rise of pop art. So you had people like Andy Warhol, who was incredibly interested in producing images on this massive scale. You take to screen printing images, he'd make an image, often from sources that he would find in advertisements or news photographs, and he'd make them into a template, so he could lay it over with different colors and make as many copies of his own work as he wanted. This was designed to be fast and easy to replicate. So in the image on the top left, you see this practice at work. They're just painting over more or less a type of stencil, a screen print, where the paint either goes through or doesn't and produces this image. And so you can use the same basic template, which you see with the electric chairs, an image that he took from newspaper photographs, and he just used different colors and different sort of backgrounds in order to make the image different over time. All of this is going on in the late 50s, 1960s. So there's this real shift in thinking about what art can be, should be, in relation to popular culture, and even among a small subset of artists, what computers and technology can do to transform and democratize art. The idea that art is this highbrow thing for the elite is coming apart. And this movement, Fluxus, pop art, all of these computer arts of the era are saying, what else could be art? What else can we start to include as art? And this is where Jasia Reichardt comes up with the idea of doing a show where machines make the art. And in 1968, that show opens. It's called Cybernetic Serendipity. And the title refers to two things. First, is cybernetics, which you know from earlier in the lecture, and two, serendipity, introducing the idea of chance explicitly into the work. Computers were working to make stuff random, but with some small degree of control. So we're going to watch a video of that exhibition. This goes for a little bit of time, but I just want to show you, this is some great surviving footage that was shot for, again, the BBC in 1968 for a news program about the exhibition.
When one goes to an art exhibition or an exhibition which involves poetry and music, we think that the people who have composed the music, or who have produced the images, or who have written the poetry, are artists or poets or composers. In this exhibition, this is not true.
Yeah, Kim, calm down. Boo, boo, da, boo.
In the first section, we have works which are produced with a cybernetic device, with a computer. That is, computer-composed and played music, computer-generated graphics, and computer texts and poems. At the moment, in one of the 4 domes, where there are music tapes lasting 12 minutes. The music is on a loop, and it's changed daily. And anybody sitting here can hear one or another type of computer music throughout the exhibition. This is an entire computer music studio which belongs to Peter Zinoviev. When Peter Zinoviev first said that his computer is a composer, I couldn't believe it. Given a sound source, the computer can be left to produce its own sequences. The Computer Technique group from Japan have taken one photograph of the late President Kennedy, and they have made 6 transformations. The computer has scanned the photograph and has turned the image into a linear image with lines pointing either towards the ear or towards the eye. The drawing machine by John Revillius is a harmonograph. It enables people who can't draw to make pretty pictures. Anybody who has a visual idea but has no talent for drawing can use the computer and express himself in numbers or in ideas and get a visual result. This is a cybernetic sculpture by Wenying Tsai. This sculpture is calmed by red light and it's activated by blue light. In the second section, we have cybernetic devices as works of art.
不，各位，不，打不，yeah, don't be shy, come on, 不，
This machine, which consists of 3 rows of different colored bulbs, responds to sound. It's by Richard Hogle and it comes from America. June Paik has 11 television sets, which he has transformed, so that one cannot see any of the programs that are going out, and yet they provide the source for some of the images which one can see. Some of these can be manipulated by the audience with magnets.
I will not meet you behind the building. You are bad, bad, bad.
So this is the era of pretty big machines. There's no off-the-shelf software like Photoshop or Premiere to help you make a movie. There's no game engines, right? If you want to make a movie with a computer, you write the code and you run it. If you want to build a robot, you build the robot. Michael Knoll. So let's just watch this because it shows you the process of what it's like to make computer art in this time.
Michael Knoll is a computer engineer who likes to visit the New York City Ballet whenever he gets the opportunity. One evening he was watching a ballet which is widely regarded as a turning point in modern dance, Stravinsky's Apollo. As he watched, Mike Knoll conceived the idea of creating a ballet with a computer, and this was the picture in his mind. As a computer expert, he was well able to translate his ideas into a computer program.
Of course, though, the really essential part of this is the computer program, which enables the individual to communicate his intentions to the computer. For instance, in the computer program to make the computer ballet, which I have here, the first part of it is concerned with setting up the instructions for drawing the stage on the automatic device that produces the pictures. The stage is shown here as consisting of 600 units on each size. So we have here, it's a list of instructions which produce a stage, which is then still in a movie for 24 frames, which corresponds approximately to about 1 second. After that 1 second of the silent stage, the individual chorus, consisting of what I consider to be the boy dancers and the girl dancers, then come on. So we see here a main subroutine, which is a little separate program that the big program transfers off to. And this little program is responsible for drawing the individual stick figures. These stick figures are made up of little line segments, which are drawn on the automatic device that produces the film as straight line segments, starting down here at this point 1, continuing up to point 2, thereby drawing one arm, continuing across with 1/2 of the shoulder, up to produce the head, down to produce the rest of the body, back up again, across to complete the shoulder, and then off to finish with the final other arm.
The completed program is transferred onto magnetic tape, and the tape in turn transmits the program to an automatic device which produces the images. These are displayed on a cathode ray tube. Just as in conventional animation, the computer film is made up of single pictures, each very slightly different. Projected at normal speed, they'll give an impression of movement. Once he's checked that the pictures are all right, the tube can be put back into the apparatus, ready for filming to begin. Facing the tube is an ordinary film camera, which photographs the images one by one as they appear. Also built into the apparatus, a developing tank, so that the film can be processed immediately after it's been taken. Finally, test pictures of single frames of film negative are displayed on this unit to check the picture quality. And so we present the first part of the world's first computer ballet. Already, a number of artists are learning from computer experts to master the techniques which resulted in this film, because they believe computers provide the most exciting possibilities at present available for experimenting with film. And now the results of these early experiments are coming in. Here's a trial run for a film title produced by a computer. This piece of computer animation, originally designed for a color film, is too complex to have been made using conventional techniques. Engineers, too, are producing strange and sometimes beautiful shapes in their computer films, like these two bodies revolving in space. This computer animation shows two bodies in an imaginary world which has entirely different laws of gravity from our own. In this film, two celestial bodies approach one another and eventually collide. An artificial satellite orbits the Earth. The satellite has been drawn as a box to show its tumbling motion more clearly. Finally, the stress on a square piece of metal is created in a computer film. Films like this, of course, are only pioneer work in a new medium. A medium where scientists and artists are going to have a lot to offer one another.
So I want to emphasize the ending of that statement. This video is not the only one that puts this out there, but remember these threads that we've been looking at. There's this movement to democratize art, to say there's new things that art could be. More people can participate in the making of art. There's this kind of revolution in the capability of display, the accessibility of computing. And so this idea that more people can be artists and that engineers and scientists can have relationships with artists and make art themselves. Even the idea that the work that engineers are making is itself a type of art, are coming together also with this idea of cybernetics, which, as we talked about, was bringing all these disciplines together. And so this line between engineering and science and this sort of idea of arts and humanities being separate is starting to become more flexible, and they're starting to exchange ideas more and more often. Not in the least because psychology and engineering is coming together in the way that people are thinking about technology and computing. But also artists have a lot to say and a lot to offer to engineers, and engineers have a lot to offer to artists. And so this is a whole new kind of interdisciplinary dialogue that is starting to take place in this time and space where Cybernetic Serendipity, the show, is running. So you start seeing things like artist labs in places like Bell Labs. Here we have a work by Vera Molnar, the drawing of lines by a machine. And so there's slight differences in the commands being used to render the same image. And so it's changing the shapes, right? And this is some of the pioneering work that you'll see in coming out of Bell Labs. And one of the videos that we have assigned for next week is another pioneer short video about her. Harold Cohen is arguably one of the first of these artists whose work really qualifies as what we would call artificial intelligence today. Now, that's a murky definition, but we'll go through it and you can tell me what you think. In the 1960s, to give you some background, Harold Cohen was a painter. And Harold Cohen had a pretty impressive resume already. He was the kind of artist who was showing their work at the Venice Biennale. And by the late 1960s, he began teaching art at UC San Diego. At the same time, he started programming computers, working on something called the DEC PDP-11, which you see over here on the left. This is not the machine that he used. This is an example of the machine that he used. And in 1972, Harold Cohen starts working on a piece of computer software, which would eventually become Aaron, all caps. And this is software that would generate its own images. Once the program was running, Cohen's art was entirely co-created with this software. And he describes his motivation. Aaron began its existence sometime in the mid-70s in my attempt to answer what seemed then to be, but turned out not to be, a simple question. What is the minimum condition under which a set of marks functions as an image? On the simplest level, it was not hard to propose a plausible answer. It required the spectator's belief that the marks had resulted from a purposeful human or human-like act. What I intended by human-like was that a program would need to exhibit cognitive capabilities quite like the ones we use ourselves to make and understand images. All its decisions about how to proceed with a drawing, from the lowest level of constructing a single line to higher level issues of composition, were made by considering what it wanted to do in relation to what it had done already. So here we see this relationship back to that Turing machine, this comparison, right? Neural networks. What's the threshold for making a decision? How do you automate that process of making a decision? And how do you automate the process of an artist making a decision about where a line should go? The first true Aaron program was created with Stanford's AI laboratory. In those days, the approach to AI was knowledge capture, breaking activities down into a series of decisions. That chain of decisions and actions was a program. A computer that made its own decisions was basically an AI. Aaron was designed to encode Cohen's personal choices about lines and arrangements into a series of rules. When it drew a line, it was able to reference those rules to determine what the next line might be. And the work varied because the starting line would be randomly placed. Today's AI images and their systems do not generally work with individual artists articulating themselves in the same way, though they could. Instead, they break down images into pixel coordinates, find repeating patterns, and then tap into those patterns to create new work. Those systems learn how to do this, using learn in air quotes here, rather than being explicitly told, the way Aaron was. And early on, Aaron presented drawings that Cohen would color in with pencils or paints. As Cohen expanded the code to new capabilities, the drawings became more colorful on their own. And these works, the lines, shapes, compositions, even colors, were generated through a program. They were not produced by the kinds of AI we see today, but defining AI, again, it's a notorious challenge. Now, as an artist, Cohen was not interested in creating an Aaron that would just make work autonomously. He could have coded it to evolve, to make changes to itself, and actually he did test this for a little while. Compared to today, though, it seems difficult to find any expressed desire for autonomous art machines during this period. Most artists, or at least with Harold Cohen as an example, was interested in the relationship. And this may have been a limit to the available technologies or a reflection of the general interest in technology at the time, but at least Cohen was interested in the relationship that he had with the machine that made images. By the 1980s, inspired by watching children draw, Cohen did program Aaron to respond to itself by starting drawings with its own sort of stray marks, and this was the closest it got to full autonomy. According to an article from the Association for the Advancement of Artificial Intelligence, in 1995, Aaron was one of the most creative AI programs in daily use. End of quote from that article. Cohen was a painter, so his idea of art was pretty traditional compared to someone like George Brecht. But he was more directly engaged in the question of machine-generated art. And in a 1974 article, he writes, "Any claim based on the evidence that art has been produced would need to be examined with some care. And in the absence of any firm agreement as to what is acceptable as art, that we would probably want to see, at least, that the art had some very fundamental characteristics in common with what we ordinarily view as art. This could not be done only on the basis of its physical characteristics. We would rather want to see it demonstrated that the machine behavior, which resulted in the art, had fundamental characteristics in common with what we know of art-making behavior by artists." He goes on to say, "We would probably agree, simply on the evidence that we see around us today, that the artist considers one of his functions to be the redefinition of the notion of art." So here there's sort of a give and take between what is the machine doing, how is it replicating the way an artist thinks, and then this ultimate question of, well, an artist is thinking about changing definitions of art. So what is this Aaron doing? And I leave this for you. Cohen considered the relationship between artist and machine as primarily driven by purpose. An artificial intelligence program behaves with purpose. As you look at how the machine's purpose is reflected in its decisions, there's a noticeable distinction between himself and his machine. Because the machine didn't invent the purpose for itself. Instead, Harold Cohen invented the machine to serve the purpose of making art. So the artist creates the machine for some purpose. And here he says the purpose is to draw lines, and the purpose of those lines is to make the next line. So Aaron drew literally from a series of possible lines, and we can think about this in comparison to what image synthesis models do today, aside from the relative size of the data that's available to them and the possibilities of what those lines might mean and how small and detailed those lines can be. They're now down to pixels, right, instead of lines. And they're not drawing them, they're drawing them on our screens. Today's models are denser. They reduce things down to relationships which can be reassembled. The size of the training data and the vastness of the parameters in that neural net certainly enhance the complexity of what they can produce. But that alone doesn't suggest a fundamentally different purpose from what Aaron did. Creativity, Cohen writes, lay in neither the programmer alone nor in the program alone, but in the dialogue between program and programmer, a dialogue resting upon the special and peculiarly intimate relationship that had grown up between us over the years. And after Harold Cohen died in 2016, Aaron was wiped out by a power surge from a lightning storm. Weird, but true. In conclusion, we focused on 1968. Marvin Minsky has promised a full artificial intelligence in place by 1978. Stanley Kubrick has us flying around the galaxy in spaceships piloted by AI by 2001. The future seemed very bright for AI because they had seen the trajectory of just a few years across the 60s. Machines the size of factories were now the size of rooms. Everything was getting smaller, denser, more complex, and the logic was eventually we're going to be able to create something completely autonomous through that density. There were breakthroughs in modeling and feedback and information science, and what we got instead was what we call an AI winter. Artificial intelligence investment moves in cycles. When there's a breakthrough, lots and lots of progress happens, and then it stalls. And when it stalls, so does the investment. In 1973, the UK government put out an investigation that said, this is a lot of hype. In no part of the field have the discoveries made so far produced the major impact that was promised, was the conclusion of the Lighthill report. This led to a suspension of support by the UK government into artificial intelligence research. In the United States, it was DARPA, the Defense Advanced Research Projects Agency, that stopped funding AI research. But that was because most of 1969 law changed the way that science research was funded. So instead of saying, we want AI, we're going to fund people working on AI, it shifted the demand for results. If you were a researcher, you had to make a proposal with specific outcomes in mind, and you had to deliver on those outcomes. So when AI consistently failed to show early results, DARPA's funding dwindled. And projects became left to the research departments of places like IBM and Xerox. And it became focused on solving management and business issues. And by the 1990s, with the birth of the internet, most research became about understanding how to coordinate communication between large groups of humans rather than necessarily between machines and humans or machines and other machines. So we saw this revolution on the internet that was basically as promising a revolution as anything that AI could dream of. And what nobody seemed to realize is that this new technology, the World Wide Web, was going to be the basis of an information revolution that would herald an AI spring by the late 2010s. Instead, we worked on flight automation software, automated teller machines, and nothing quite as inspiring as cybernetic serendipity or robots that could paint. Until now, when it seems as if overnight that that's exactly what we have. And in the next session, we're going to look at the recent history of artificial intelligence and creativity. Thanks.